All right, so when looking at this power question, we have to show the voltage across and the current through each element in order to submit a valid gradable response. We do this because we have to prove that the passive sign convention agrees with the results we calculated for power. This image illustrates passive sign convention for power calculations. It states that positive power is equal to conventional current flowing from higher voltage potential to lower voltage potential multiplied by the voltage. In terms of voltage and current, this is the same passive sign convention that we use for nodal analysis. All right, let's focus on this problem on the right. Besides voltage polarity in current directions, there's no constraint as far as what method we need to use for solving the problem. So we can use whatever we want to make this problem as smooth as possible. Let's start with labeling our voltage polarity and our current directions. My current arrows are going to stick to the same convention. Current flows from higher voltage potential to lower voltage potential. Same thing for my resistors. I'm going to set these up in a way that predicts that the current is going to flow in a circular path like this. That might not actually be the case, but remember, when you set these polarities, it's a theoretical prediction. A good next step is inspecting the circuit visually to see what sorts of known values, constraints, and relationships you can extract from it. Let's label the nodes. So if we take a look at V1, this voltage source, we see that we have a positive terminal at node VA. That's going to set node VA to 3 volts. Let's keep that over here too. If we look at this voltage source, we get some information as well. Although we don't know what VB and VC are equal to right now, we know that VC should be equal to VB plus 1. As you can see, we have a positive terminal at VC and a negative terminal at VB, indicating 1 volt difference. Upon further inspection of V2, we also notice that we have a convenient supernode. This is because we have VB and VC being 2 non-reference nodes that share this V2. After inspecting the circuit to understand what your known values, constraints, and relationships are, you have a decision to make. You can use nodal analysis or mesh loop analysis to solve this problem. Now, since we have a convenient supernode and we also have another known node voltage, VA, if we use nodal analysis, it can give us a lot of information. So let's start writing KCL equations. Let's start with KCL at node VA. My first term is going to be IV1. This is how we're going to symbolize the current for this voltage source. I'm going to say plus VA minus 0 over R1's value, which is 1 ohm. And since I'm going to follow this convention here, I'm going to set that equal to VB minus VA over R2's value, which is also 1 ohm. Remember, voltage is the difference between 2 points, and you must make sure your nodes are in the correct order that agree with the passive sign convention. So if VB is at the positive lead, it must come first in the KCL term. Let's go on with some algebraic simplification. Although we know what VA is, be careful about substituting too soon. It can lead to some confusion. So for now, we're going to keep VA as a variable. Simplifying further, by subtracting VA from both sides, we get that IV1 is equal to VB minus 2VA. Let's save this for later. Our next KCl equation is going to be at our supernode. Now, to follow the same convention that we talked about before, we're going to take a look at the currents that are leaving the supernode and the currents that are entering the supernode. The current that is leaving the supernode is conveniently the same current that is going through R2. So for that term, we're going to use the same notation. VB minus VA over 1 ohm. And we're going to set that equal to the current entering the supernode, which is going to be conveniently the value of I1, 1A. So now that we have these two KCl equations, we should see what substitution can do for extracting more values. I'm going to start with this guy right here. Since I know what VA is, what can be gathered from the fact that VB minus 3 is equal to 1? We should gather that VB must be equal to 4 volts. Once we have this, it's a good idea to see what we can do with substitution into this equation here. We have IV1 being equal to 4 volts minus 2 times 3 volts for VA. This gives us that 4 minus 6 is equal to negative 2, and that IV1 is equal to negative 2. Now, if we go back to the relationships and the constraints that we talked about earlier, we see that VC should be equal to VB plus 1. So now that means that we have VA, VB, and VC. 4 plus 1 is equal to 5. Now let's clean this up a little bit. Alright, so with all this cleaned up, we see that we have all the node voltages and we have one current through IV1. So if our end goal is to find the power through each of the circuit elements, we're going to want to find the rest of the branch currents. Let's start with our resistor R1. From Ohm's law, we know that I is equal to V over R. So the current through R1 should be equal to 3 volts over 1 ohm. It's going to give us 3 amps. If we look at R2, we're going to do the same type of calculation. This time, we have to make sure we include both voltage points in our difference. We're going to get 4 volts minus 3 volts over 1 ohm. It's going to be equal to 1 amp. If we try to get the current for IV2, we can do a mini KCl at node VC, this one right here. According to KCl, with the convention up here, IV2 should be equal to I1, which is 1 amp. As far as IV1, we've already gotten that current as negative 2 amps, as you can see from the equation to the left. And from the current source, we know that I1 is equal to 1 amp. Alright, so after organizing our calculations, we can see the flow of the problem a little bit easier. The last step is going to be solving for the power through all the elements. Let's start with R1. We have that the current is equal to 3 amps. Ohm's law tells us that the voltage is going to be 3 volts minus 0 times 1 ohm. That's going to give us 3 volts, which is going to give us 9 watts. Let's look at R2. We have 1 amp for the current, and Ohm's law tells us that the voltage should be equal to 4 volts minus 3 volts times 1 ohm. That's going to give us 1 volt. And we'll have 1 watt. For I1, we know that I1 is equal to 1 amp. But let's look at the voltage. If we refer to the polarity that we set earlier, we must calculate the voltage as being 0 minus 5 volts at VC. This gives us negative 5 volts. If our voltage is negative here, our power is going to turn out to be at negative 5 watts. This is where our passive sign convention comes up. Although it's negative, it's a correct answer, but it's only correct because we've shown that our polarity requires us to calculate the voltage this way. Let's look at V2. We have that the current is 1 amp. We also have that the voltage is 1 volt. This gives us 1 watt. Let's look at V1. We have that the current is negative 2 amps. And our voltage is 3 volts. This is going to give us negative 6 watts. Again with passive sign convention. Although it's negative, it's a correct answer. But it's only correct because our current direction shows that we expected the current to flow from this higher potential to lower potential, but this negative symbol is actually telling us the current flowed this way.